Good afternoon, everyone. Thank you very much for taking the time to participate in this presentation today. By way of introduction, my name is Janine Barbacane, and I'm an account executive within Confluent's public sector organization that supports the Department of Homeland Security and the Department of State. With me today, I have Andrew Jacobs, who is a solutions engineer within our public sector practice, and Mike Peacock, who is also a solutions engineer within our public sector practice. So how does Confluent fit within a zero trust framework, and how can Confluent help government agencies achieve a zero trust security posture? Well, at its core, a zero trust architecture has a simple tenet: never trust, always verify. So with Confluent, which is built on the open source platform Apache Kafka, Confluent can help government agencies perform the actual verification of the data that needs to occur within a zero trust architecture. The reason why Confluent can support the verification of the data is because Confluent has become the de facto standard for event logging and processing due to its ability to capture, process, and analyze observability data in real time and at scale. So for purposes of this presentation today, we are going to demonstrate not only how Confluent fits within a zero trust architecture and how we can support the various use cases that have been identified by the ATARC Zero Trust Working Group, but we're actually going to demonstrate how to collect, process, and analyze observability data in real time from a variety of different data sources, while leveraging existing investments and tools such as SIMS and SOARs. So before I turn it over to Andrew Jacobs, I'd like to just mention a few things. First, please don't hesitate to interrupt during the presentation and ask questions. Second, we will include our contact information at the end of this presentation, so please don't hesitate to reach out with any follow-on questions. And finally, we will be posting this presentation as well as additional collateral on the ATARC Zero Trust Working Group huddle site, so please feel free to reach out and reference that material in the future. And with that, I will turn it over to Andrew Jacobs.
Great, thank you, Janine. And thank you, everyone. I appreciate the time to be able to introduce Confluent to you today. I'm gonna go out on a limb and assume many of you probably have not heard of Confluent, but you likely have heard of Apache Kafka. And so let's kind of start by talking about what we do, which is putting data in motion. So if you go back to 2010, our founders of Confluent were working at LinkedIn, and they had a challenge of needing to integrate large amounts of data in real time. Searched the market, didn't find a solution that could really do it. And so they created Kafka, which they then donated to the Apache Software Foundation. And so it became known as Apache Kafka. And then they went on to create a company called Confluent, which has a mission of putting data in motion. So we provide support for Kafka, as well as we add additional enterprise features that enterprises need in order to make it successful. So if you think about Red Hat and what it is to Linux, that is what Confluent is to Kafka in many aspects. And as Janine mentioned, a lot of our customers have been leveraging Confluent in order to capture large amounts of observability data. So as you can see here, the usage of Kafka has really ballooned since it has been introduced. And so you can pretty much find it anywhere. And we have a large amounts of customers across all of these different verticals, as well as several across the DoD and civilian agencies. So if you're not familiar with the phrase data in motion, or maybe you're not familiar with Kafka and what that means, here's a really quick example that hopefully resonates. So imagine you're on a trip, COVID's over, or you're traveling, and you need to take a taxi to get to a place, a hotel, something like that. And in order for that to happen, you have to have information, right? So if you open up your app and you go to Lyft or Uber, your location and your destination have to be matched very quickly with drivers that are in your area. Your route has to be planned. You have to get an estimate for how long it's going to take you there. the pricing has to be calculated. You're also going to want to know where your driver currently is, what the reputation of that person is, and so on and so forth. And so you've got a lot of different pieces of information that all have to work in concert with one another in real time in order to facilitate that experience. Once you get to your destination, your ride gets paid for. All of these things happen automatically with a click of a button, but they're really powered through this concept of what we call data in motion or event streaming. So that's a quick example of what that means and how data in motion makes these types of experiences possible. Now, of course, we're going to talk about what it means to zero trust, but hopefully your gears in their mind are already turning about how that may be beneficial in a zero trust framework to have a whole bunch of different pieces of information that are flowing in real time at large scale where decisions need to be made, right? So let's step back and talk about kind of the world that we're all familiar with, which is if I have a piece of data, what am I going to do with it? And chances are you're going to put it inside some sort of a data at rest technology, right? Like a database. And a lot of the key components for enabling zero trust, including like SIMs and SOARs, are built on top of this model. So they'll ingest something into a database, search index, file system, object store, and then people will analyze that information. So there's a lot of flexibility there, but it's typically a batch-based process where they do that, right? And so the more information that you have, the more tools that you're leveraging, the more data that's being generated, the more expensive all of that gets, right? And so there are consequences for that to the mission, to everything else. And so when you want to integrate these things, it also leads to a very brittle architecture, right? Where you have a whole bunch of different technologies that may or may not speak with one another. And someone has to figure out how to get them all to interoperate well together. And so this becomes a major pain point when you're trying to solve your mission, when you're trying to get data and bring it together in real time. And so instead of doing it kind of this traditional batch way, Confluent has a different paradigm where you have a real-time data platform. So you've kind of taken your data infrastructure and you've reimagined what it can do, where information and events are flowing across all of your different applications, your SaaS layers, your cloud systems. And this is very much something that is being embraced by a lot of people in the commercial sector and the government sector. And here, like, your data is no longer static, right? So it's not that, hey, I've got information, I put it into my database, it's there, anyone can query it whenever they want. Data is in motion. So as things are happening, decisions can be made with it. It can be passed along to other groups and people so that real-time actions can be taken on that. So the fundamental technology components that make this possible and really which are a part of Kafka and Confluent are, number one, you've got to have a way to publish information in, and then people can subscribe to it. And this is really great. This is a well-known design pattern, right? Where you have decoupled the people who are creating the information from those who need to consume it. Second, you need to be able to store that for a certain amount of time, which you can specify, right? So with a lot of traditional messaging systems, when they send something, as soon as someone has consumed it, it's gone. And whatever they did with it, it will determine whether or not that becomes available later. Not so with Kafka. So you can have multiple different consumers all getting the same feed of information and doing whatever they need to with it, which is really nice, because if you have a new product or technology or use case that needs access to that data, they can simply subscribe to that feed and get all of the information that they need to there. Third, as nice as it is to be able to share information, like I've got a bag of bytes and I'm going to put it into Kafka and someone else is going to read it, it's far more powerful to actually be able to process that information, to do something with it, right? to calculate a risk score, to be able to aggregate it, to filter it, whatever needs to be done. And those capabilities are a part of the platform to be able to process and analyze these event streams as they're happening. So those are kind of the foundational core tenets of Kafka, and then Confluent, of course, adds a whole bunch of things on top of Kafka. I'm not going to go through all of these, but at our core, we make it easier for developers to be productive. We make it easier to manage and operate this. And we have a whole bunch of security and other types of features that allow you to build these types of event streaming and real-time data sharing architectures. And so that's really what we do at Confluent. And with that, you can power, obviously, a whole bunch of various use cases. We've listed a bunch here. And there's a very wide gamut of how people will use our technology. So you may be looking at this and kind of wondering, all right, I kind of get it, but how is this relevant to zero trust? Like, Confluent doesn't do anything with identity management, endpoint management. We don't do micro-segmentation on networks. We don't do a lot of things that a lot of the vendors that you've seen do. So what does this have to do with zero trust? And for us, it comes down to this, right? One of the core tenets of zero trust is understanding what's happening. So if you can't verify, if you can't see what's going on, how can you verify and protect it, right? So that is one of the core tenets. I mean, if you go back to Forrester, when they introduced the term of zero trust back in 2010, they mentioned the need to be able to continuously monitor your zero trust ecosystem with security analytics, right? You look at NIST 800-207, it's the same type of thing. Like, continuous monitoring is one of the key parts to know whether or not you're being successful in what you're trying to accomplish. And so with Confluent and our ability to handle large amounts of data, it becomes something where there's a solid value proposition because of all of the new data that is going to be generated with all of the different components of zero trust that need to operate in real time with one another. And they can't wait, right? They need to make decisions, not hours, minutes, or days later. You've got to make decisions in real time. So with that, I want to kind of outline what we see as some of the key challenges that agencies may face as they are going along their zero trust journey. So first of all, there are going to be a whole bunch of different environments, right? Could be hundreds of them, depending on how things get deployed. And so you're going to have cloud environments, on-prem environments, edge environments, and there will be very different capabilities and limitations there, both from an infrastructure perspective as well as like from a security perspective, what you're allowed to actually do and deploy within those environments. And so if you're out at the edge, for example, you could have very poor connection speeds, right? You may not want to send a whole bunch of logging data from the edge into some centralized system because you don't have the infrastructure to do so, or it would cost far too much to use that bandwidth. And so whatever zero trust architecture gets deployed has to consider all of these different environments. That's kind of first. The second, there's a whole bunch of different technology that's already in use, right? And that has to be accommodated. So agencies aren't going to throw out old solutions. They have to support what they have and protect it. And they need to be able to have visibility into what's happening at many different layers across their network and the application stack and endpoint. So has to have a way to be able to support multiple different types of technologies. And they've already invested likely in some security capabilities, right? And they're going to start with some of those. Now they may get rid of them. They may purchase new ones, but they're going to have to start with what they have and continue from there as they go on their zero trust journey. I mean, you can make the case, perhaps there's a program that can stand up something separately, something greenfield, but by and large in the federal government, I think it's a fairly safe assumption that there are large technology investments that have to be maintained. Next, there isn't going to be a silver bullet to solving this problem. I think we can all agree on that, right? Because zero trust is a set of principles that go far beyond just technology. It's not that you can say, okay, in order to deploy zero trust, we can just buy this one vendor solution and be done, right? It's going to involve multiple different solutions, and all those solutions are going to have a way to work with one another, which takes me to the next point, that when you've got a bunch of different solutions that are all working together and you are working with a framework that provides only principles, you really need some interoperability standards. And so some of the vendors have those built in, right? They'll build in integrations with other types of things, which is nice, but you can also, you need to be careful about that because you want to avoid vendor lock-in as well. And so being able to have access to all of that information across a variety of different solutions, to be able to share it and really decouple your data information from all of the different solutions who need it is a critical capability. And just to follow up on this, the real-time nature of the information that is required to be able to feed into the policy engine and the trust algorithm is central to all of this, right? You can't wait those days, weeks, and months in order to do that. And so you need to have a solution that can see across many different pieces of architecture, many different environments, where you'll have different vendors who are working with different data models, different APIs, and you need to somehow bring all that together to be able to observe it. And so you may be thinking, okay, Andrew, I get it. That's what a traditional SIM is for, right? Our solution integrates with a SIM, and so we're just going to send it all there. And yeah, that is kind of the solution that people go with and think about, right? So why do people then still come to Confluent or leverage Kafka to be able to help address these challenges and modernize their cybersecurity posture and help enable zero trust? So there are a few things that we do that provide a whole lot of value. And we tried to articulate them here on this slide. The first, you can take data from anywhere and bring it into Confluent. And you can do that in real time. So you can forget about batch pipelines or any of that kind of stuff. So as soon as an event is generated, that notification can go into Confluent, and it can be made available to anyone, right? To multiple different solutions, as you can see on the right-hand side of the screen. Second, once we have it, we can improve the quality of that information. So we can do really anything that's necessary. You can filter it, you can curate it, you can join it together with other pieces of information. You can provide contextual awareness that improves the quality of your insights that piece of information has, and that really is going to help enable better decision-making and to be able to find where things have gone wrong much faster. Third, we make it easier to reduce the data indexing, analysis, storage, and other costs so that you don't have to make this trade-off between visibility and costs. And we've seen that where, as people are designing their systems, they'll look at different data sets and say, okay, well, we're going to take these, but these other data sets over here, while valuable, they are so voluminous. If we actually put them into our SIM, it would bankrupt us because it would take our entire budget to accommodate that much information. And it's not that they don't want it, it's that it's a whole bunch of information and they don't know in advance whether it's 95% of it, 99% of it can be ignored. And so it's really low value data. And you don't know that until after you've paid for it, right? Until, in many cases, it's gone into the system and you've already, foot the bill for that. And so some of those choices have to be made. And then finally, as you're putting information into Confluent, instead of having like a direct connection between whatever zero trust component you're using and your observability tool, that's a point-to-point connection, right? Which means those solutions are dependent on one another. So there has to be integration that's been built somehow. With Confluent, we kind of provide a decoupling mechanism where you have your information that's being generated by your zero trust solutions, and it can go into this intermediate phase where we can enrich it, we can filter it, we can rationalize the amount of data that you actually want to send into other solutions. We can do real-time alerting and other things with it. And we can send it really to any solution you want downstream. And that provides a lot of flexibility. So if you have, again, new solutions that you need to deploy, who need to leverage that data, not a problem, super easy to do, right? So your architecture becomes far easier to manage and rationalize because the most important parts of that, which are really like the data, are free to go wherever they need to. And so you're not locked into these point-to-point connections. And so how do we actually accomplish this? Well, connectors are key, right? No one wants to write a bunch of custom code. I talked about connectors with other products. So we obviously have a large suite of connectors that make it very easy to get information from wherever it's being generated into our system. And so you can, take security event, authorization events, sensor data, transactional events. You can even take like network data, PCAP data, NetFlow data, and you can put that all into Confluent. And so, we have customers who handle trillions of messages per day and generate petabytes of data, and they do so effortlessly in real time, and it doesn't break the bank. So the next thing is, okay, great. So data's been generated, it's coming into the system. We need to do something with it, right? We need to provide value. We need to transform that somehow. And so Confluent provides the ability to mask, filter, normalize, enrich those events so that you can detect threats, so that you can provide information back into your trust algorithms, to your policy engines, to other places where you may need it. And so we have a suite of different capabilities that make this very easy to do. And so you can use declarative ways like using KSQLDB, which has a SQL-like syntax, or you also have the ability to deploy machine learning models as well, which can be executed in real time to be used for forensic analysis. And so this combination of capabilities really can meet any needs that you have to be able to take that raw information in, not lose it from a data fidelity or governance perspective, but be able to enrich it, transform it, put it into standard normalized formats, and really make it fit for purpose so that it's helping to accomplish the mission that you need. And as I mentioned, one of the big components of this is cost reduction and savings, right? Because if you don't have to, if you can make decisions about the data before you are paying to put it into a SIM or into other solutions, that enables you to do so with confidence and enables you to tackle and use other data sets like PCAP data and others that are going to have a large amount of data, but you can handle that load of traffic that they're going to be putting on the system without having all of the downside effects from a cost perspective. So that's going to lower your overall costs. It is going to help you to preserve it. So if for whatever reason, in order to meet some of the mandates that are coming out from the White House with their executive orders, you need to take that data and you need to keep it safe. It becomes very trivial to do that with a system like Confluent. And really, you've got this freedom of choice, right? So with this decoupling mechanism, you have the ability to put that data wherever you need. So if you're even generating data at the edge, right? So you could have, because you can deploy Confluent anywhere, it can be deployed at the edge on very minimal hardware that still has great capabilities. So it could be capturing all of the data that it needs to there, doing the processing out at the edge, right? To be able to filter, transform, make decisions about that data. And then you can just send like the high value parts of that data up to some centralized place for decision making so that it can be leveraged by your zero trust system with, of course, access back into the system with the full set of data at any time if you need it. Of course, you can send the whole set of data as well if you want to. We've got very powerful capabilities that allow you to take multiple different deployments across geographic areas and have them seamlessly operate as one kind of data fabric or data mesh. So that's one of the one of the great capabilities. And in fact, this slide talks to that, where you can really deploy this wherever you want. So it doesn't really matter what kind of environments you have, public cloud, private cloud, hybrid cloud, whatever you want. We've kind of seen it and done it all, and are able to sync all of this data together in a way that makes sense for you and is helping to fulfill the mission. So these are technically how that gets done. We have a SaaS service, which are in the process of FedRamping. We've got operators and hardened containers. We're actually are available in Iron Bank to help facilitate containerized deployments, or you've got kind of the highest DevOps option of being able to just take direct RPMs, debs or tarballs and deploy them wherever you need to. So there is a ton of flexibility in the platform to be able to meet whatever kind of deployment methodology you'd like to. So really quickly, I mentioned we have deployed these type of architectures across several different customers in the federal space, including across the DoD and many different civilian agencies as well. I wanted to talk just quickly about Intel because they're a public reference of ours, and they had a similar challenge where they had a whole bunch of different solutions and they didn't have a great way to have that holistic view across them because they had a whole bunch of brittle integrations that were point to point and would fail over time. And so they kind of built up a lot of technical debt with it. And so with Confluent, they kind of created this abstraction layer for upstream and downstream systems that required a lot less work for them to maintain. It allowed them to very easily add in new data sources from different applications that they were doing. They would filter, enrich, aggregate, and normalize their data in real time. And what that really meant for them is they were able to do a lot more for a lot less. So they were able to dramatically decrease their costs for doing that while improving the overall experience and the observability of what they were able to actually see to enable faster decision making. So from a deployment standpoint, this is kind of what a standard Confluent deployment looks like. The brokers are where all the data gets stored. And so it's horizontally scalable, which means you've got disaster recovery and everything else built in. Schema registry allows you to register what your data should look like, and it can power some of the transformations. So you can evolve those schemas as your schema changes. So that is an optional component that can be very handy when you're doing data transformations. KSQLDB and Kafka Streams are two of the data processing engines that allow you to actually put your business logic in a declarative form and have it be executed in real time. Kafka Connect powers all of the connectors, and Control Center provides visibility to what's going on. So all of these different components of our system scale out individually. So your compute and your storage are actually separated. So if you just need more storage, you can add additional brokers. If you need more compute, you can add additional nodes on your KSQLDB or Kafka Stream side to be able to power those types of capabilities. And we are licensed on a per node basis. So each node is licensed that way. So I think this is Jerry's slide, which we stole and kind of put in orange the things that we either do or we help enable. And so again, we are not directly related to any of the other core parts of Zero Trust other than really the observability, the monitoring component and being able to take action on what's happening inside of there based on the information that we're seeing. So if there aren't any questions, we can jump into a demo. You guys can actually see what this looks like. My colleague, Mike Peacock, is going to be running the demo, and what we're going to be showing you doesn't align specifically to any of the different scenarios, but it is going to show you how you can take different data sets, how you can bring them into Confluent, how you can modify them, and then how you can send them off into other places. And so with that, I will turn it over to Mike.
Great. You want to stop sharing there? Yep, there we go. Okay. Give me 1 second. How about that? Can you see that, Andrew?
Yep.
Okay. All right. Yeah, I got everything moved around. All right. So basically, I'm going to show a demo. It's a live demo, so there's guaranteed to be some messing up going on here, but so bear with me. But it's a live demo of basically everything Andrew just walked through. So we're going to show the ease of connecting new data sources and also pushing data to downstream applications like Splunk and Elastic. We're going to show real-time threat detection in the streams of data. Show you how you can decrease overall costs. And when we talk about costs, we're not talking just a monetary cost there. We're talking about cost of performing indexing and querying on that data if you're pushing too much down to say a Splunk or something like that. Or even feeding a policy engine's trust algorithm as well in real time. We'll show examples of stream processing using both KSQL DB, Andrew called out, and Kafka streams. So what we have is it's a completely Dockerized environment. It's running on the ATAC AWS environment, ATARC AWS environment, and it includes a full stack of Confluent. It includes Splunk and Splunk data generators. We have TCP replay that's replaying packet information that was collected during a data exfiltration event. We have Zeek network sensor data, the ELK stack, Elastic stack. We also have Duo running, simulating a multi-factor authentication. And then we have the Confluent Sigma stream processor. I'll go into that. It's an open source project we have right now that's built on Kafka streams to look for threats and patterns in real time. All right, so I'm going to start off. What you're seeing here is our Confluent Control Center. This is our web interface that gives you complete administration over the environment. All the topics and user data and everything else is all in one-stop shopping here in the UI itself. So if we take a peek at the cluster, really gives you insight into everything I just said, your brokers, your topics, what kind of connectors are running, KSQL DB and things. We'll jump all into that during this demo. But let's focus on the topics first. What a topic is just a way to compartmentalize your events in your system. So it's much like a message type that you're pushing around your environment. In this sense, you see all of the different packets of data that were coming in. So we have DNS data, the Duo data that I called out. We have a bunch of the Zeek data here, so connection, HTTP, SSL, and everything else that you expect when you're collecting network sensor data. So I'll jump over to the connectors. Andrew called them out. We have well over 140 different connectors. What I have right now is just a single connector that's already running. What this is doing, we'll come in the demo later, but all this one is doing is pulling information. It's a CSV file that has domains listed in that we're concerned. So concerned domains that will come into play when we do some additional processing on there. But what I'm going to start off by doing is adding a syslog connector, just really to show that how easy it is. No code option here to connect to data that you already have in your system. So prior to doing this, I already connected syslog. It's being exported to a UDP port. So as I add this connector, all I really need to do is change it to UDP for the listener, and then set the port to 5140. Everything else is already set for us in this configuration file. But you can see there's a lot of parameters you can set based on your environment if you need to. What the UI also does is build that configuration file so you can get a good snapshot of what you're looking to do. So if I launch that, you'll see it start off here in a minute or so. There we go. I'm going to add one more connector. This is a Splunk. It's a Splunk S2S connector. It's pulling from a Splunk data forwarder. In this case, all the parameters are already good by default because it's using default Splunk settings. So we'll launch that too. All right, there we go. Sorry. So let's take a look at the topics. We'll peek back at that. I'm going to start off by showing the DNS data. Again, this is coming from Zeek. So Zeek's pretty popular. You get a lot of different data from Zeek. In this case, it's DNS information, and we're consuming a lot of that information right now. You get a good throughput here. This is real-time data being pushed through. If I were to pause that, take a peek, what you see is everything you expect from Zeek DNS. The originating IP address, the responding IP address. We're going to focus really on this query field, which is like what the user is actually looking to do. I mentioned there was a data exfiltration event, so we'll look at how you can identify any kind of bad actors potentially using the query to push some data that may react differently on different networks. So that gives you an idea what DNS looks like. I'll jump back and I'll show the syslog data that we're collecting, right? So as soon as I see it, there we go. Same thing. Pause that, and I'll show some unique characteristics here that we do with our connectors. So what comes in is the raw message, and we're able to dissect that out to partition and put some structure to the data. But what's important is, even as we build that structure around, we still include that raw message. So when we do eventually push this data down to a SIM tool, there's no need to reconstruct all that information and provide that raw message. It can easily just be indexed by those SIM tools downstream without any other action required. And let's check out Splunk lastly. If we have that, it takes a little bit to spin up sometimes. It's not there just yet, but it will pop in for later on. But basically, it's the same idea. That Splunk data that we are receiving has the raw data associated with it and the structured data also. All right, so now we're going to start looking at how we actually do some stream processing using both KSQLDB, and eventually we'll move into Kafka streams. So I'll start with our KSQLDB editor. In here, you can actually add just SQL-like syntax. So how SQL is built, KSQL is built, it's built on top of Kafka streams. So it provides, what the value really provides is SQL-like syntax. So in the cases where you may not have a development team that can write a Java application, for instance, or you just want to do quick querying of data, this is pretty powerful in providing that capability for quick stream processing. So let's show an example of what we're doing here. So you have the topics, is, like I mentioned, a way to compartmentalize information or events. Streams are built on top of topics. And once you have a stream created is really where you can start providing that enrichment capability, whether you're aggregating or filtering or what have you. So in this case, I'm not going to go through everything, but what we're looking to do here is the data coming in is JSON. So we're looking to provide some structure around that to create the stream. You see all the fields that we called out in the connection topic itself. We're pulling from that connection topic, and then we're writing to a new stream called con_stream. And the same thing with DNS. So I'll go ahead and run that query. You'll see that they are now created, and that's a persistent query. So that's going to continuously run as we get new data coming in. And I can show you an example of doing a query on that. So what we're doing is querying the DNS stream. If you look at, again, here's the contents of JSON. We're going to focus on that query field, that query attribute. And all we're going to do is count any unique query that comes in there. So you can see that's happening. No, that's happening in real time as data is coming in. So in this case, you see the DNS query and the number of queries that count there. So it's continuous aggregation going on. Now, that may or may not be valuable, but what could be valuable is if you apply sort of a windowing aspect to it. So the fact that you're getting these counts alone may not provide value, but if you apply a window that says, if I got a DNS hit, say within a 10-second or 30-second window, and it was the same query, then there might be some bad actions there. You might just want to provide an alert, and that's a capability you can do here. We'll show an example of windowing a bit further down. All right, so that just shows a quick way to create a stream and do a quick query. So let's do a bit of enrichment here. Let me copy this in, and I'll show you what I'm doing. All right, so again, we're creating a new stream. If we look at what we're doing here, we're actually joining two streams of data. So one is from the connection stream, and one is a DNS stream. And why we're doing this is because the DNS stream alone provides, the DNS data, but it doesn't provide the packets of data, the bytes associated with that. That comes from the connection topic. So we're looking to join both, again, in real time. We're joining the DNS with the connection and providing more of an enriched topic here that shows the DNS data along with the packets requested and replied back. The other thing we're doing is providing some geospatial information. So what you see here for get geo for IP is a user-defined function that's part of KSQL, and you can create your own custom UDLs or UDFs. But what this does is it actually goes out and retrieves information based on the IP address, and it provides some geo information based on that. So we'll show an example of that real quick, what that looks like. So let me show you something here too based on that now. So this shows a graphical view of the streams and tables and everything else that are created. I like showing this because you can see the lineage of how things were done. So in this case, like I said, we're joining data from DNS and a connection stream and providing an enriched topic called rich DNS. So if we peek at that, you can see what we have in here is that geospatial information, the latitude and longitude from that IP address, the country of origin, United States. Some of the other information missing, but it will be there for others. And then you also see the bytes, both requested and replied. So a bit of enrichment in that case. That's pretty cool with the geo information. All right, a couple more examples here for using KSQL for enrichment, and then we'll move on to some other examples. So I mentioned what we're pulling in is that the watch list information from CSV. So we're going to create a table. A table in Kafka world is much like a database table. It's a materialized view of the streaming data, but you are getting that in real time. Andrew also mentioned the persistence that's built into Kafka. So what's powerful here is that when I create a stream or a table, I have the option to get the real-time information that's coming as of now and building a table or stream from there, or I can look back at the earliest time that I was getting that information and build it from there. So in this case, I'm going to build a table that will look back to the earliest, my start time basically, and build that table of information from there. And again, I'll show you what that looks like. So here's our table. And this is basically just the CSV data we pulled in earlier. It shows the domain. This is a watch list domain. So anytime we get a DNS hit that was using that domain, we want to flag it. That's the gist of what we're trying to do here is build an alert. So we'll create a stream based on that. It's building from the table, and we want to know if anything on the watch list is now from that query, like I said. So we'll run that, and then we'll just do I'll do a query, and I'm going to limit it to just to show you that you can also just limit what you're querying on. And there you go. So we had this DNS, which was on our watch list. Now this can be pushed down to any kind of end stream application for alerting or warning to maybe a SOC analyst or whoever is receiving that. And I'll show one more example of alerting using that duo data, the multi-factor data. So in this case, what we're building is, I don't want to have a stream that's giving me anomalies if a failure occurs for somebody logging in. Obviously that happens often, especially when I'm trying to log into something. But I would be curious to know if if I had multiple failed logins over a window, right, over a certain amount of time, then maybe that's a bot that's trying to get on the system or something like that. So in this case, we're building a stream that says, I want to know if there's multiple failures within a 30-second window. I'm going to count that. I'm going to aggregate it and push that out to a stream. So we got that going. And now, again, that may not be valuable. It may be too much information that you're providing to a user. So I want to create a stream based on that. And I want to know if it's any kind of suspicious activity. So multiple failures within a 30-second window may not, again, provide value. But if it happens more than 10 times, is what we're showing here, then that could provide, some sort of anomalous behavior or malicious intent. So we're going to provide that now as a failure and an alert downstream users. So if I go back to my flow, you can see now here that I have the failure stream. I'm creating a suspicious failure rate, and that will provide any kind of information here that I did have. Say in this case, we had 20 failures within that window that we provided. So flag it as anomalous and provide the SOC analyst or whoever, again, downstream is the ability to go back and look at the data to see what's actually going on. So a couple examples there of providing real-time alerts using that data in stream. All right, so I'm going to move on. That's KSQL. What we have here is Kafka's the Confluent Sigma. This is built on, if you guys have heard, the Sigma project. It's an open source project, and what this is really providing is an ability to abstract rules for your downstream for any SIM tool that you're using. But really, the intention is to not be vendor locked into the rules that you're providing. So a lot of times using Splunk or Elastic or anything like that, you're creating thousands and thousands of rules to be able to identify anomalies. Sigma takes it to a higher level. It's a domain specific language. You can generate a rule at this level and then convert it to your downstream applications. So you can take a Sigma rule, convert it to Splunk, or Sigma to Elastic, or there's a ton of different converters available. So what we did as an open source project is take that ability to define a Sigma rule. I'll show you an example of what that looks like. Take the Sigma rule syntax and apply it in the stream. So in the background, we have a Sigma streams application running, a stream processor. It's receiving the DNS topic data, and it's applying any of these rules that we create here in the stream. So it'll identify and write it to a new topic based on that. So if I publish that, it's now in topic information. I'll go back and jump to that real quick. You can see Sigma rules. And there it is right there. Has the rule that we just created and we published. I go back here and I can look at that data in real time. Now this UI here it's not required. It's just a way to visualize the information and find it a bit easier to manipulate the rules and visualize the data coming in. So what we have here is what you see in gray is all the DNS information coming in. And you can see the content here. Now the rule I just created was looking for, go back to that real quick. The syntax here, again, I'm not going to go into each field, but really what we're looking to say is look at that query field and the DNS topic. And if there's any characters that are greater than 180, then flag it as anomalous. Now, that alone may not be enough. In this sense, we don't have any that are flagging it, but just to show that it works, let me go back and make it ridiculously low. I'll set it to 8. Republish that topic, come back here, and you can see now that basically everything is being flagged as an anomaly. So again, not valuable showing it's working here, but here's the content here. And again, what this visualization is showing is that all that information would have been sent down to, say, a Splunk or an Elastic, and it may not be valuable information. So that cost there to either send it or, again, to perform indexing on it is what we're looking to save here. So I'll show one more example. This is more of a time-based example. So we're looking to do, again, look at the query field and that DNS topic. Anything that's greater than or at least 50 characters. In this case, we're looking at windowing. We're saying we want to know if it happens more than 10 times in a 5-second window. So let's go ahead and publish that. We jump back here and start looking at the data in real time, and eventually, yep, there we go. We have a hit. Again, this shows the value right here of all that information being sent to Splunk. That's gray, but really the meaningful information is in red. So if we peek into this, we can see that here's our DNS data, and there's definitely something going on funky here in the DNS query. The domain is Mr. Haha, so he's definitely trying to do something that's malicious. But again, that alone will be now pushed down to your SIM tool to provide some analysis to look and see what's going on there. All right, so the other thing that we built from the Sigma processor is the ability to do regular expressions. So now this works with Splunk. This is the Splunk data that we're receiving from the forwarder. We're going to look at Cisco data. So let's provide this as my source. I'm going to build a regular expression. And what this is doing is now taking that sort of unstructured data and applying structure to it. So then I can do analysis downstream. So what I'm going to do is write this to a firewalls topic, just creating a new topic based on this incoming set of data. And then I'm going to build some custom fields. Now the value of this is that if you want to do something in your downstream tool that may not be part of the data set, you can add that in here and it'll get written to that. So you can do, comparisons or whatnot once you get down there. So I'll add one more for the indexer. Again, this is probably something critical in a SIM tool that you can use for indexing purposes. So let me submit that. And now we have that data is being written in the firewalls topic. Probably passed it. Here we go. Yep, there we go. All right, so we'll use that later on once we actually show Splunk. We don't have much more to show here, but so we're wrapping up. How we doing on time? Andrew, what time do we have till?
I think we're good on time. It's
Okay,
another 20 minutes, maybe, if I'm calculating correctly.
All right, should be done by then for sure. So I'm going to focus on Splunk here, right? So we have talked about earlier using that Splunk connector to receive data into Confluent. So we're going to build a stream based on that topic that we're receiving. And I just want to filter out certain, this is a specific sensor, right? So this might be a noisy sensor that's producing a ton of data, no value add. In this case, we're going to filter that out so we're not sending that information down to Splunk. So if we run that, we now have a filtered. Splunk doesn't exist. Hold on. See, live demo. There we go. Forgot to create the streams. All right, now we have the Splunk stream being created from the Splunk S2S events and another stream for just the Cisco information, pulling that out. And now I'll filter out the noisy producer here, noisy sensor. There we go. So let's go back to the flow. It's getting complicated here, but again, showing how quick you can build all these different processors. We now have a good amount of queries going on all real time here. So pulling from Splunk, we have the raw data with including Cisco, and we also have the filtered information all being written out to different topics. So we're going to eventually ingest these both in the Splunk and do a comparison for savings and things like that. All right, I'm going to create a couple more stream processors, streams here. And again, we're going to use these. So what I'm looking to do is I had that firewalls topic that I was creating from the regex expression. I'm going to create a stream based on that. That's running. And then what I'm going to do is show how we can compress data. So there's a lot of duplicate information coming in that topic. As you can imagine, it's repetitive in some nature. So we're looking to really compress that information So if we look at the firewalls topic, and we want to take all the data that we're receiving that firewall topic, but I really want to compress it. So looking at a 60-minute window, I just want to add a count if it's duplicate. And by checking to see if it's duplicate, I'm grouping the information by the attributes in that topic. So it's really just going to provide any kind of unique event that occurs. And where it's not unique, it's going to increment that count for a 60-second window. Again, this is compressing the data. So rather than sending all that down to a Splunk or an Elastic, we're going to now compress it. Let me run that query. And I'll show what that looks like over in Splunk. But first, I'm going to add a couple more connectors, right? So we showed how easy it is to add source connectors. Sync connectors are the same way. So rather than adding that in through the UI here, I'm just going to show a quick way to do both Splunk and Elastic. So Splunk was just there, and I will add Elastic. So you can see from here, from the connector perspective, we have both Splunk is producing raw data and heap data. It's the aggregator topic that we just added is being pushed down, and also the filtered data to Splunk, and Elastic's receiving that rich DNS information that we already produced. So now this is, again, that's how easy it is to take data out of Confluent and push that down to these SIM tools. If we jump over to Splunk real quick, I'm not a Splunk expert, so let's see what we got. There we go. So this is showing two sources in Splunk now. It's both the data that we just pushed. And what's really interesting now, if we start showing, again, I'm going to point back to that compressed data. If you really want to show some savings, we can say, we can build this query right here that says, show me the savings that I'm now having based on the raw data that I'm pushing through, and compare that to the compressed data now. And I'm going to show that, what that looks like. And there you go. You can see that based on that compression that we did, we were able to save between 98 and 99% of the data that's now being pushed to Splunk. So definitely value add there from a cost perspective. Again, not just monetary, but also the performance, the CPU, and everything else you would need to do for indexing. So lastly, I'll just quickly show Elastic. We're already pushing it because I created that connector. We have the rich DNS data now available. We go back and visualize that real quick. There you go. So now that's as easy as it is to get information in real time down to Elastic and Splunk, and also show a lot of value for what you can do in the stream prior to even pushing it down to any of these downstream tools. And that's the demo. Any questions? All right.
Great. Well, thank you very much for your time today. And once again, please don't hesitate to reach out if you have any follow-on questions. And this presentation will be available in the ATARC Zero Trust Working Group Huddle site, as well as additional collateral pertaining to Confluent. Thank you, everyone.
Thank you so much, Confluent, and all of these recordings will also be posted to YouTube as well. So if you want to go take a look at our ATARC YouTube channel, they'll be up there in the next few days or so. Thanks, everyone, and have a great weekend.